Every few years, my mom brings up the idea of putting solar panels on the roof of the old chicken house at my grandma's farm in Ontario. And I'd also like to thank my mom for taking the photo behind me. Her idea makes sense because it's a sunny south-facing roof. But the building is 100 years old and wasn't built to withstand the weight of solar panels, which could add 1,000 pounds or 450 kilograms to that roof. Also, like all roofs, it has a limited area. So the maximum output of a solar system is determined by the efficiency of the solar panels, which is also limited. So between these factors of weight and limited efficiency, suddenly solar just doesn't make sense here. But what if it's not the building that isn't suited for solar panels, but solar panels that aren't suited for the building yet? That's what I'm trying to change with my research, and it comes right down to the solar cell, the fundamental component in a solar panel. Conventional solar cells are made from crystalline silicon, which is fragile and requires glass casing to protect it, which adds weight. Silicon also only absorbs certain colors of light, which contain only a third of the energy in sunlight. And modern solar panels have pretty much maximized this efficiency. To overcome these issues, our research group at UBCO is developing a new type of solar cell made from two different materials called perovskites and CIGS. We can make these materials from chemical solutions that can be deposited in extremely thin layers, only a micron thick. And because these layers are resilient to bending, they can be used on lightweight and flexible substrates. Also, perovskites and CIGS absorb colors of light in different parts of the solar spectrum, so we can stack them on top of each other in what's called a tandem architecture in order to capture up to 30% more energy than a single layer of silicon. Our lab has already developed highly efficient perovskite and CIGS solar cells separately. My role is to put them together in a tandem. In practice, this involves creating chemical sandwiches in the lab and measuring how well they absorb light and generate electricity. Although my work is only in the early stages and there are challenges in scaling it up and ensuring long-term performance, in the future, these cells could provide the basis for solar panels in lightweight and space-constrained contexts, like building walls and portable power supplies. And I hope one day that will even include the roof of the chicken house at my grandma's farm in Ontario. Thank you.